Thank you. My name is Tim Marler from the Virtual Soldier Research Program at the University of Iowa. And I have a couple things I want to focus on, present, on one hand, some tools that we have integrated into the Santos human model with respect to ergonomic analysis. But then also talk about the idea of existing tools and standards and new tools and standards. Right now, I think in terms of ergonomics and human factors, there's a number of different tools like NIOSH lifting tables, Liberty Mutual lifting analysis that are based primarily on experiments, data, lookup tables. And those are critical. Those are the tools on which some standards are based, and we can't lose those. But as new fundamental R&D matures, I think there's a responsibility to start looking at that for new tools, for new standards. So I want to walk through some of the things that are in Santos in terms of both of those cases, and then touch on a couple of case studies with respect to armor design and then seat analysis and design. This is one such, say, current existing tool for spine shear and compression at the L4, L5. As Santos predicts postures or is manually positioned in a posture, we automatically calculate the shear and compression at L4 and L5, and a variety of different ways to display that. This is work that was developed in collaboration with US CAR, particularly with Jim Potvin. And so in real time, as you move him, or if you were to predict various postures in real time, you'll get automatic update in terms of that, the shear and the compressive forces on the spine. In terms of the NIOSH lifting tables, this is another common tool that's now integrated within Santos to position a box, say at an initial position, a final position, and then what is the recommended weight, or excuse me, what percent of the population could conduct that task given the weight of the box and the distance it's going to travel. It also will give you the recommended weight for that task if it's not specified initially. With similar applications, we've aggregated the Liberty Mutual analysis data and implemented that so that you can sequence a task for Santos. And this is kind of a neat capability that will show up in the next tool as well. I can take motion capture. I can take motion prediction, which Kareem will talk about in another technical section. I can take a series of posture predictions and create a sequence. Here's a simple one. Then based on that sequence, we will automatically look at that, look at the joint angles in that avatar, and pick out key postures, key tasks that relate to the Liberty Mutual data. This is a squatting position. This is a reaching position. Then based on some input from the user in terms of the frequency, the time, we automatically spit out a report, again in terms of the percent population or the amount of weight that could be lifted for that particular task. So again, a common tool, but it's critical. This is one on which standards are based. Engineers, ergonomics experts use this. Energy expenditure, based on the common GARG analysis or GARG approach, does similar things. I can have a series of tasks, and then this gives you a little more detail as how it automatically analyzes that sequence. And there are a number of them you can call up, or the user can create whatever that sequence of tasks may be. And you put time points in there where you want to analyze it. And then it automatically looks at that and says, okay, here are the tasks that are relevant to energy expenditure analysis. The user can then modify those as they do here. Confirms, refines it. And there's a list, a drop-down menu of tasks that you can select, again, that correspond to standard energy expenditure evaluation. And the user inputs loads, sometimes timing, and then you can get an automatic output and the amount of energy that's expended based on experimental data, lookup tables, this kind of thing. given that information, on the left here you have the energy expenditure, average energy expenditure rate for that particular task. That becomes input into another standard tool, thermal threshold, and tells you what is the work cycle, what percentage of that task or of your time can be spent working, and how much time do you need in rest. For this particular task, it's suggesting it's relatively easy, not a lot of rest is necessary. So these are existing tools. I think these are probably familiar to most of the people in the crowd that are in the Santos software. But again, it's data-based. And one of the things that we're trying to do as we develop these new tools is we look at the current state-of-the-art, which is maybe familiar to most of you, this idea of motion capture. And you can do phenomenal things with this, specifically when you're looking at a single individual and see exactly the nuances of that motion. And that's how this movie Avatar worked. A key component of this is it's data in, data out, except it just looks a little different. It comes in the form of numbers in terms of motion capture data. It comes out in the form of an avatar, a character, a digital human model moving that represents that motion capture data. We want to take a slightly different approach. We'd like the input to be a hypothesis, and this applies to posture prediction, and again it applies to dynamic motion prediction, which will be a topic of a later talk. So maybe I think when you're doing reaching tasks, or maybe when you're walking, I think you minimize the torque in your knee. I then may model that. I make a mathematical model that I can test, I validate, I modify that. But when I'm done, I understand where the data came from. I have a better idea of why you do what you do, how and why people perform the way they do. And it's presumably a robust hypothesis, so I can modify parameters, alter the problem, and rerun it without having to go back to the lab. So when we talk about physics-based, mathematical-based predictive models, this is what we're talking about. And then I'm going to run through some examples of tools based on this for ergonomics. This is how it works. It's optimization-based, so we're finding the joint angles to optimize various performance measures. Joint torque, maximum joint torque, discomfort, joint displacement, a series of different performance measures that are used to evaluate tasks, such as those that you might do to test body armor, which I'll show you an example of. Subject to some constraints. Target constraints, I want my elbows on the chair, I've got to touch certain things as we talked about in the previous conversation. Range of motion, collision avoidance, don't reach through the computer screen as you go to get something behind it. But as I want new things, as I want to take this foundation, be it for posture, motion, whatever you're simulating, it's just a matter of new constraints. I can include static equilibrium, so now I can predict postures based on force. Not just analyze what's going on in your joints if somebody pushes on you, but predict how you react to those forces. I can then model stability. I can then incorporate strength and fatigue, right? Not just as a post-processor, but to see how you pose and move as a reaction to changes in strength and fatigue. So let's look at some of that. In terms of the performance measures, this is, I think, a very powerful ergonomics tool that transcends the typical reach envelope. So not only do I show you what you can and can't reach, but I show you the green zones. What are the most comfortable areas to reach, say for fingers or for your arms, and your body and your legs. I then take that information and impose it perhaps on existing geometry. Or I just look at around the avatar if I'm way high up on the design stream and just starting to try some design concepts. We call this zone differentiation. It's a very powerful ergonomics tool for upstream design, but also for downstream analysis. Then in response to some needs that Caterpillar had, we took that same tool and can we bring in geometry or an area you're working with and just get a score. So what happens here is you'll get a, sitting in a car, the user will highlight areas that are critical. I want to look at the steering wheel, the stick shift, and the radio button. Okay? And it will automatically perform that same zone differentiation, but just on those points you select. and it'll give you a score, an aggregate or average score for each of those parts, and then your total environment. So a lot of times as you provide the user with tremendous amounts of feedback, sometimes I just want a score that can substantiate a decision I've got to make on this layout, on this part design, or on this kind of body armor or seat design. And that's what we've done here. I apologize, it's a little fuzzy on the projector. But for each of the parts that you've analyzed, you'll get an aggregate discomfort score, and then it averages all those for a total of what was about 40. Now, the precise value for those is irrelevant. What's relevant is the relative value. As you try out different systems, different designs, we're able to compare those. Then I talked about external forces. So now as I want to do posture prediction, we've heard a lot about that, what we call static analysis, and having to manipulate that avatar. Well, what if I can just predict what all those joint angles are, or predict how your body reacts if you want to touch a certain point? But also now consider forces. So I'm going in and I'm making this backpack heavier and heavier. And I'm not just positioning Santos and saying, give me the joint torques. This is a key point. I'm saying, here's a load. You, Santos, tell me what your position would be in reaction to that. And then as we do this, although I'm not showing it very explicitly, we can also give output in terms of stability. How close are you falling over? How strong is your balance, so to speak? And as well, you just saw in real time, I can get joint torques and range of motion. Then once if I'm calculating those joint torques, one of the things we're developing in response to a need of a body armor manufacturer is as I go through various tasks that I typically do to test out this body armor, how can I move? Can you give me some feedback in terms of torque? And this is what you see in real time. It says dynamic, that's not quite accurate. In this context, what that means is just real-time motion with the interface. There's no impact or inertial considered here, although forces are considered. And as I apply external forces or different postures in real time, I get all the joint torques back. And then I present them on the avatar. I think the colors are graded by 10 to 20% of your maximum voluntary contraction for each of those joints. So again, as I predict a posture, I conduct some task to be able to get this feedback. Certainly for propensity injury is a very useful tool. Now, one of the constraints I showed in predicting posture was strength. Now, typically, if I'm predicting how I grab something, and I think of each of my joints as a little motor, right, that produces torque. That's how we model strength. There's a limit on that. And I can set a limit and say that my elbow can only produce so much torque. But that limit varies with the angle. Okay? So what this shows is I can actually implement those strength curves, maximum torque versus angle, and see how that affects not only the output in terms of joint torque, but the posture. So I could say, lift that box as if the slider has a percentile strength, 5th percentile strength, 75th percentile strength, and I can actually see the difference. So I'm not just using it as a post-processor. I'm incorporating the indication that you're very strong or not so strong in your predicted performance. Run that again. And the slider that it's a little hard to see is percentile strength. On the right, you'll see joint torque for each of the joints. He'll get set back to his initial position, but then predict the posture based on that variable strength. Again, this was some work done in coordination with O&R, and they wanted to see, can you perform this task? And if you can, how would you do it differently if you were a little weaker, you're a little stronger, or the things you're dealing with are a little heavier? Then I want to implement static fatigue. And so this is actually integrated as well for static cases. And what it will tell you is, how long can you hold that wrench above your head? And when you start to get tired, which joint is going to fatigue first? And this is based on some work that Dr. Frylaw and Keith Avon from our strength and fatigue team did, extending Romert's curves. So essentially making joint-specific Romert's curves. So as I change a position, a posture, or eventually you'll see as I change a load, which joint fatigues first, and approximately how much time till it fails. And we're working now on intermittent fatigue, and then dynamic fatigue is, of course, the most challenging problem. How do I fatigue as I make a motion over and over again, or as I make a motion, rest, make a motion, and rest? And based on some unique predictive capabilities we have, these are some new tools that we've implemented for ergonomic analysis. Oh. That was my backup slide for detailed questions. And another capability that we have based on that optimization approach, if I'm saying, how do you perform? You perform in order to optimize some objective function, some performance measure like discomfort or joint displacement, subject to all those constraints. What's that objective function? It's not always the same. You don't always try to minimize all the torques in your body. So here what we tried was pick up a box using 75% joint displacement, where you gravitate towards a neutral position, and 25% joint torque. And it didn't work. But then when we change that, and we say, you know what, maybe your torque is driving your performance more than that tendency to gravitate towards a neutral position, then it hit that validation effort spot on. You'll see some intersection between the box and the knees, and the very lower fidelity, higher computational speed run was used in this study for collision avoidance. And at the same time, I can take a look at spine, shear, and compression for these sorts of things. So now we have all these performance measures, all these potential drivers. One of the efforts we're working on now is using neural networks to predict for different tasks what drives you. For these kinds of tasks, it tends to be 30% torque, 20% energy. For other tasks, it may be something else. So we're really looking at what's going on underneath the surface. So now a couple of, I won't go through the whole case studies, but just touch on some things we're doing that sway towards human factors or ergonomic analysis. One is body armor, and this focuses, so far, this is ongoing work, on rigid body armor plates, not yet the soft armor, and not yet the soft tissue, but we look at things like restrictive volume. What volume of that armor is restricting your motion? What's your total coverage? What's your balance throughout a task? What's the weight? Your range of motion, your performance, and of course your torque. And we looked at a couple systems. Typical, the OTV system is just the chest plates, and then these were two prototype systems provided by an armor manufacturer, and they sent us the geometry, call it C plates and B plates. And we can get this kind of output to automatically, in near real time, calculate the coverage. Of course, OTV had the smallest coverage, where, as you might expect, the armor configuration for B and C, the more plates had higher coverage. And we can look at the weight. It's always a balance between coverage and weight. So given 10 pounds of armor, body armor, where should I best put that? In terms of mobility, what percentage of your total free range of motion has been restricted? With the chest and back plates, not as much, considering this is ongoing work and we're making some algorithm updates. And you can see with the additional plates, that range of motion restricts. Then we can also start to look at your performance during various tasks, arm raise forward, arm raise sideways, etc., etc. For this particular study, we use something what we call, or what could be referred to as quasi-static motion simulation. It's a series of interpolated postures. as opposed to full motion prediction. And in each of those postures, we'll get feedback in terms of joint displacement, in terms of discomfort, in terms of total joint torque. And in general, what we're finding for the different cases, there's not a whole lot of variability for each of these tasks that we modeled so far, and we're modeling additional tasks as well. And when you have the rigid armor, what we're also finding is what's more critical, or what has to be considered when you look at range of motion, human factors issues, is all the additional stuff. Right now, these plates are fixed on the body, and we're working on a method to sort of approximate soft tissue. But there's also soft armor. There's clothing. There's soft tissue. And that needs to be considered as well. And one of the biggest obstacles is all the stuff in addition to body armor. Your clips in front of you that keep you from run into your steering wheel. So we're taking this kind of technology and extending it to equipment that hangs on your body as well to get a better idea of your encumbrance, the volume that restricts you. Now we can look at balance as well, using the kind of analysis tool that I showed you earlier. And as I run out of time, I'll run through this. This is actually like a 3-minute clip, but I can predicate what you'll see here. This is a study actually done by Mr. Steve Beck for Caterpillar, where we brought in Caterpillar geometry and we brought in an avatar. And they wanted to look at where should we put the foot pedals, where should we put the seat, where should we put the handles. Now, if I want to look at all three of those things at once, and I want to look at them for a suite of percentile avatars, conceptually it's not too hard, but it's a pain in the neck. I have to call in an avatar, I have to look at the handles here and get some feedback. Look at the handles here, get some feedback. And if I put a 5th percentile female, as you see, maybe she can't reach the pedals. So what do I do then? There aren't too many tools to analyze all those components concurrently for concurrent engineering. And this is one of the things we can do just using that zone differentiation tool. And I can start to look at the total range of motion for the body. I don't know that I can speed this up, but if you bear with me for about 2 more minutes, you'll see the whole thing. And we can input the seat index point as stipulated by the manufacturer. That'll coincide with the hip index point, hip reference point for the avatar when we bring the avatar in. And then it will automatically adhere to certain constraints, or at least try to. Have the elbows on the arm, the hands on the handle, the feet on the pedals. And this is talking about the seat index point. Predicated again. Once I put the avatar in there, what I want to know is, what's your total, say, discomfort? And what's your total discomfort as I move your whole body around based on that range of motion of the seat? And then can I plot your discomfort somehow based on those different points where I've moved the seat? And I can look at the green zones for the seat or the red zones. And you'll see that shortly. And then with this particular avatar, if you want it to touch the joysticks, the pedals, you just can't. Even if you extend the seat to its full range of motion. And we can see that very quickly, nearly in real time. So I'm articulating through the full range of motion of the chair. And the typical approach at this point now is to just do a finite set of postures. And what we're going to analyze is thousands, thousands, potentially millions of different postures, and then plot the results for that. So as this finishes out, it pauses so you can read those if you happen to be in the front row. In summary, it's critical to retain the tools we have now, the tools on which certain standards have been based. They tend to be experimental-based tools or data-based tools. However, we have to push that forward with respect to ergonomics and human factors. And as these new capabilities, say a zone differentiation, posture prediction with external loads, or other capabilities you'll see from other universities and companies today, those standards, those design processes and criteria have to be updated accordingly. And this is one potential example where the typical approach, the typical criteria really aren't sufficient to do just variable anthropometry justice. So while this finishes out, I can field any questions just for the sake of time. Yes, sir.
Looked fantastic. Great job. You're showing one grip to be analyzed. You said you don't do dynamic grip. So if I'm holding on to the box and I want to put it inside another box, repositioning hands, are you analyzing that and then reassessing the forces as you, if I'm holding onto the side and I want to set it into something, if I release, is the box going to drop?
Okay. So there's two things when I said we're not doing dynamics. We do dynamics, a lot of them. I'm just not talking about it. In terms of the hand, now what you'll see here, excuse me, one second, is these are the green zones. If I just look at the range of motion on that seat, the green shows you if I put the seat in that position, those are areas where, say, discomfort is very, discomfort would be minimal, right? So comfort would be high. But then if I extend the range of the motion of the seat, you'll see a more extended analysis. Now back to your question. So we do dynamic analysis. In terms of the hand, we have a lot of work that does posture prediction for the hand, grasp prediction for the hand as well. And that posture capability for the hand, how you would hold a box, updates the same way that you see the avatar update. So the short answer is yes, we do that. Just not shown here.
Thank you very much, Tim.